Okay, let's start. So our homework list there has changed dramatically, right? We just have two assignments here. This one we haven't started talking about. We're right in the middle of talking about integration using inverse trig functions. So we saw some examples last time, and we're going to look at some more examples today. And then I think we'll have time to start this section. So this is our last homework in sort of the first part of integration techniques, and then we're going to take a little break here to do some applications of integration, so you can see how integration can some of these integration techniques can be applied actually to certain problems, and then we'll come back and we're going to do some more advanced integration techniques. Okay, so so for a couple of weeks here, a few weeks here, just applications of the integration techniques that we've already learned before we learn some more. So we'll finish off this notes today and see how far we can get into this one. So the homework dates here, these are movable, right? So I've just got dates attached there. So you need to be working on this homework, and we'll see where we're at on Wednesday. And then I just posted this new one and put a date on it. But again, that one too we can alter as we need to, right? See how far we get into the notes today. I posted the on the Blackboard page the answers to the test, so you can take a look at the answers to the test. It's going to take me a little while to grade the test, so I'm not looking promising for Wednesday because of my schedule this week on having the test back, so it probably will be Monday. So I'm sorry for that delay. I usually like to hand them back immediately, but just have other intervening responsibilities this week, okay, that's slowing me down. So so be patient. As soon as they're graded, as I mentioned, I'll post the grades in WebAssign. But in the meantime, you can take a look at the answer key. Okay. All right. So that's kind of where we're at right now here. Any questions so far? I don't know if y'all been working too much on the integration using the trig functions. We still have some examples to do there, so some of those problems, probably the earlier problems are kind of straightforward, but some of the later problems maybe still not be equipped to do those until we look at a few more examples here in the class. Okay, you've been keeping up with your homework very well. I don't know, did that translate? Y'all took a long time to take that test. Were y'all not comfortable taking the test? Don't know yet until you see your grade? Did you do the review? Yeah, if you didn't do the review, then you probably were caught by surprise, right? Okay, on the test. That wasn't a unnecessarily difficult test. Okay, so don't think that that one was really hard and the other ones are going to be easier. That's probably about the level of difficulty of the tests, okay, in the class throughout the semester. So that's kind of what you're looking forward to. All right, so so keep coming to class, right, and keep working on your homework. All right, so that's how you're ultimately going to be successful here in the course, and as the opportunity presents itself, right, keep going to tutoring. I know Taylor was not here today, so Taylor is not in class, so hopefully she'll be back on Wednesday. Okay, all right, so we're going to start just again where we were last time in the notes, okay? So we were just looking at examples here of integrating using inverse trig functions. So here's the next example we're going to do, but again, just to remind you there are the really the key formulas, right, that we're going to be applying here when we're integrating using inverse trig functions, right? And so remember what you're looking for which is almost always the case, right, when you're doing integration, is the form of the integrand, right? Okay, so if you come across an integrand that fits one of these three patterns, or it's close to one of these three patterns, then that's a good signal, right, that you might be able to integrate that using an inverse trig function. So if you have square root of difference of two squares, then that's a signal, right, that you might use an inverse trig function. Or if you have not a square root in the denominator here, but just the sum of two perfect squares, okay, then if you see that pattern, then might be able to integrate that using inverse trig functions. Now, sometimes, as we'll see in examples today, these patterns may not exactly present themselves when you first look at the problem, but with a little bit of experience, you'll see that you can sometimes manipulate the integrand using algebra. So you can rewrite the integrand using algebra and get it to fit into one of these patterns. All right, even though it doesn't initially look like it's going to fit. Maybe that applies to this example that we're going to do right now. Maybe. Okay. All right. So we want to try to integrate the reciprocal here of the square root of e to the 2x minus 1, right? So dx over square root of e to the 2x minus 1. So, again, when you first look at that, you might be thinking immediately, right, ooh, I have a square root there, and so in the denominator, and 1 is a perfect square, right? Okay, 1 is obviously 1 squared, and so this might be one, right, where we can apply inverse trig functions. So if we look at the these formulas up here, right, which one is this closest to? Which one is this integrand closest to of these three formulas? Well, you might say 1, right, okay, because that's difference of two squares, but notice there's a fundamental difference between the quantity under the square root here and the quantity under the square root here. Here, a is a constant, right? So you would have constant squared minus u is the expression. So it's constant squared minus the expression squared. But notice this is the other way around, right? Okay, here's the expression minus the constant, okay? So, and that becomes important. So this one doesn't quite fit, right? That one obviously doesn't fit, right, because this doesn't have a square root in it. So our only other choice is this one, right? Okay. So that's kind of close because here you have so here we would be using arcsecant, right, to do the integration. So you have expression squared minus constant squared. That's what we want. But notice some things are missing, right? In this formula, you need also the expression here in front of the square root, which we do not have, right? Okay. And the other thing I'm wondering about is what expression is squared here, right? E to the 2x. How do we write that as some expression squared? Well, let's work on that first. So how can I write e to the 2x as something squared, right? 1 is obviously 1 squared, right? But what about e to the 2x? Yeah, see, some of y'all are already not paying attention, and that's what translates into low test scores, right? Okay, it's kind of your mind drifting through space in class, right? Okay, that won't get you out of calculus 2. That would be sad because that means you'll have to change your major, but that's life. All right. So, so any ideas there, right? Okay, on how we can write e to the 2x as a square. Yeah, that's right, okay? You can just rewrite that as e to the x and then e to the x squared, right, okay? And because of the way exponents work, right, that rewritten version will be equivalent, correct? Because remember, when you have a power of a power, you multiply the powers, correct, right, to simplify it. So e to the x squared would be e to the 2x. So it looks like here we're kind of off to a start, right? We might let our expression here, u, be e to the x power, right? And then, of course, our constant that's being squared here is 1, right? So that's going to be the value for a. Now, I still have this issue of, where is this expression outside of the square root going to come from, right? Okay? But Well, let's try doing the substitution and see what happens. So maybe something lucky will happen. Maybe it won't happen. Okay, right? But maybe something lucky will happen here when we do the substitution. All right, so let's do that. So let's see. Du dx is going to be what now? Yeah, that's easy. So that certainly makes it fun, right? Du dx is going to be e to the x power. So when we solve this for dx, what does that end up looking like? Is that du over e to the x? And, oops, not e times x, but e to the x power, right? Now, Taylor was telling me, but this is a common problem. Many of you are still confusing integration with differentiation, right? So you've got to be careful about when you're doing either one of those, right? Okay. Here we're differentiating, right? Not integrating, all right? But the ultimate goal of this problem is to integrate, okay? Right? So this is the integration problem. This is just part of the substitution, which is differentiation. That distinction now is going to become critical in a few weeks when we start doing more advanced integration techniques, okay? And in those more advanced integration techniques, we're going to be doing a lot of differentiation and a lot of integration simultaneously. Well, when I say a lot, it'll be some, okay, simultaneously. And if you are being confused about when am I differentiating and when am I integrating, you're going to get hopelessly lost in those techniques, okay? All right, so well, let's do our substitution now here, right? Okay, so what's that substitution going to look like? Well, obviously, right, under the square root, you're going to put in u for e to the x, right? So that's u squared. Here we still have, of course, the 1 squared, right? And now the dx is du over e to the x power. But you know, you don't want to write this as a complex fraction, right? You don't want to write this smaller fraction inside of this larger fraction. So the easier way to write this integrand is you can keep the du in the top, but the e to the x can come down here, all right? So that's equivalent. So I don't want to rewrite that whole line, so let me just write it like this. So I have du over e to the x, right? But what is e to the x? That's u, right? Okay, so here while I have e to the x, right, I can continue my substitution and put in instead u. And then we're in really great shape, right? So we kind of got lucky there, but of course we kind of helped ourselves too, right, by carrying through with the substitution. And notice now that exactly fits the integration pattern that you want, right? Okay, that is the integration pattern for using arcsecant. So in fact, we can do it right here, right? Okay, we can immediately now write down the antiderivative. So let's see, what's that going to be according to our arcsecant formula? It's what, 1 over a, right? So that's nice. That's 1 over 1 times the arcsecant of the absolute value of u. So that's that little catch you have to remember, right? It's going to be absolute value of u over a, but a is 1, right? And then plus the constant. And now you just have to undo the substitution to get your final answer. 1 over 1, of course, is 1, so I can drop that. So this is arcsecant of e to the x power, the absolute value of that, well, over 1, so I don't need to write the over 1, right? So we can just write down arcsecant of absolute value of e to the x power plus a constant. But actually, you can simplify even further, right? Because e to the x power is not ever negative. Remember, when you graph e to the x, the exponential function, it's always above the x-axis. It does not have any x-intercepts. So it's not even 0 ever, much less negative. So the absolute value bars are irrelevant there. You don't need them in your final answer because this quantity is never negative anyway, all right? So, so you can drop those. That's nice from the final answer there. So we just have arcsecant e to the x plus a constant. So turned out to be a really fairly simple antiderivative, right? Okay, well, not sure how simple that antiderivative is. It involves arcsecant, so that makes it kind of complicated. But it wasn't difficult to arrive at, right? Okay, once we carried through with the substitution. Okay. All right, so I have a video for this example, which is in this homework. So I'm gonna let y'all look at that video. Before you look at the video, though, you can sort of tell how things are going to proceed, right? Which one of your inverse trig functions would you probably use to integrate this? Arcsine, right, okay, because here you have a constant squared, that's 2 squared, right, minus that x is an easy expression, right, so you have the expression squared. Now, this one's a little bit complicated by having the x plus 2 there in the numerator, okay, so you do have to do a little bit of extra work. If this were just 2 in the numerator, that would be easy. You would factor out the 2, correct? But the x plus 2 makes it a little bit more complicated, so there's a little bit of extra steps here to integrate this example. You can watch those in the video. Okay, so the link to that video is in the homework assignment, this homework assignment. Yeah? No, well, I don't know what WebAssign will do, but I wouldn't count it wrong. It's just superfluous, right? You don't need to write the absolute value bars there. Okay, yeah. So again, don't forget about these extra examples, right, that you can look at in the homeworks. So they may be beneficial for some of the problems. All right, this one now is a little bit harder, okay, because this looks like, I don't know. All right. So I think maybe our initial thought here might be not an inverse trig function, right? Because that doesn't seem to fit into an inverse trig function pattern. The closest it comes to maybe is arctangent, right? But that doesn't look like a sum of 2 squares to me, at least initially, right? So I don't think, at least at the start, it doesn't look like arctangent's very promising for integrating this. If you just had x squared plus 7, though, if the minus 4x were not there, then that would be a lot better, right? Okay? 7 is not a perfect square, but you can certainly write it as a perfect square. It's the square root of 7 squared, okay? But that minus 4x in the middle just screws everything up, all right? So that's kind of a little bit of misdirection there. Now you might try just immediately just a direct substitution without worrying about the arctangent function or the inverse trig functions, correct? You might say, okay, I'm just going to substitute for my denominator, because that's what we frequently have done here, right? At the beginning of the course is just substitute for the denominator. But see, that doesn't get you very far at all, because unfortunately, the derivative of your denominator is kind of complicated. It's 2x minus 4, and so that means that dx is du over 2x minus 4. Is that right? Or is that the other way around? Yeah, du over 2x minus 4, and if you substitute for dx there, it just doesn't work out very well at all, okay? So so that kind of is not going anywhere either, all right? Okay, so let me show you what we can do, okay? So since this doesn't really look like sum of 2 squares, right? And this direct substitution kind of just results in a mess. Here's what we're going to try to do. So I'm going to go back to thinking about the arctangent function, and I'm going to try to write this as the sum of 2 perfect squares, okay? So, again, if this were just x squared plus 7, that would be the sum of 2 squares. But it's the minus 4x that's messing things up, all right? So here's how we can rewrite this denominator as the sum of 2 squares. So what I'm going to do is group the x squared and the minus 4x together, okay? And notice I'm putting a little space in here because I'm going to add something into that parentheses. But I'm going to group the x squared and the minus 4x together, and then I'm going to keep the 7 sort of segregated here, off to the back. All right, so I'm going to write plus 7 there, outside of the parentheses. Now, here's what my goal is. I want to add something into the parentheses so that I'll be able to factor this expression as a perfect square. Have y'all ever done that before? You have. You may not have remembered doing that, okay? So what I'm trying to do is I'm trying to add a constant, a number, into this parentheses so that this will factor as a perfect square. Do you know what that process is called? Completing the square. That's completing the square, right? Okay. So probably you practiced in the past for other reasons. Probably didn't do it for integration for sure, right? Okay. But for other reasons, you practice completing the square. That's a useful process sometimes. Okay, for lots of different problems. All right. So let's remember how we do that. How we complete the square. So what you want to do is take the middle coefficient here, the minus 4. All right, the reason I'm calling the middle is I'm getting ready to put something at the end, so this will be in the middle. So I'm going to take the minus 4. You just go off to the side here and do this. And I'm going to divide that by 2, and then I'm going to square that. All right, so of course, minus 4 divided by 2 is minus 2, right? And then I square that, and I get positive 4. So I'm going to insert here, that's why I left room, I'm going to insert a positive 4 into the parentheses. And now what I claim is going to happen here in just a second is this is going to factor as a perfect square. I can factor this expression, and it will factor as some quantity squared. Now, however, you have to be careful about what we just did. Notice in the denominator I added a 4, right? So you cannot just do that, okay? Because that changes the problem. So you have to compensate for that, okay? So since we added a 4 in parentheses, I'm going to turn around and subtract 4 outside the parentheses, okay? So I want to add and subtract the same quantity. So that's what I'll do. I'm just going to subtract 4 here. So that really is the same denominator because I added and subtracted the same number, but it looks a little bit different now, right? But it's really the same denominator. Now, how does this factor? Can y'all see how to factor that? You're guaranteed it's going to factor. So how does x squared minus 4x plus 4 factor? What is it? This, of course, is 3. Yeah, it's x minus 2 times x minus 2, right? Yeah, this factors as x minus 2 times x minus 2. But the easier way to write that is x minus 2 squared, which is a perfect square. See, okay? So see, now notice, wow, you've got a nice denominator now, okay? Because it's the sum of 2 perfect squares, all right? 3 is, of course, not really a perfect square, but we can think of it as a perfect square. That's the square root of 3 squared, right? Okay, and of course, this is a perfect square. It's the quantity x minus 2 squared, right? So, see, this now fits in to the arctangent antiderivative formula, right? Okay, the arctangent integration formula. What's our a here? What's the constant that's being squared? No, not 3, but square root of 3, right, okay, because 3 is the square root of 3 squared. So your constant is square root of 3, and then what's our expression? So what's the u? It's x minus 2, right, okay. So we're going to substitute u for x minus 2. And then again, the constant that's being squared is square root of 3. All right, let's do the substitution now. It's real easy to do. So u is x minus 2, so that means du is so easy, it's 1. All right, okay? So du and dx are really the same. So dx is really just the same as du. And now this is u, so I have u squared, right, plus, and then, remember the a is square root of 3, so I have square root of 3 squared. And now you can just integrate it immediately, right? Okay, because that's the sum of two perfect squares, or the reciprocal of the sum of two perfect squares. So we integrate that using arctangent. Let's see, what does that arctangent formula say? You take, what, 1 over a, right? So it's 1 over the square root of 3. Just to remind you here, there's that arctangent integration formula. So it's 1 over the a, and then arctangent of u over a plus the constant. So I have 1 over the square root of 3, and then arctangent of u over the square root of 3, and then plus my constant. Now we just undo the substitution, right? So it's 1 over square root of 3 arctangent of u, which is x minus 2, right, over square root of 3, and then plus the constant. This one doesn't have absolute value in it, so you don't have to write the absolute value. Yeah?
You just put the square roots at the bottom in the denominator?
What now?
You just leave the square roots in the denominator instead of multiplying them and leaving them on top?
I just need the square roots in the denominator. I'm not sure what you're asking me.
Can you like simplify it? Like this?
Oh, like this? Oh, yeah. Well, yeah, you can. That's called rationalizing the denominator if you don't want square roots in your denominator, but I'm not really obsessed by that. So this is fine if you leave it as 1 over square root of 3. Okay. But now, again, all right, so yeah, we have to think about what how WebAssign's going to grade you. So how do you rationalize that if you want to get the square root out of the denominator? Yeah, multiply top and bottom by square root of 3, right? And so you'd end up with square root of 3 over 3. Same thing, okay? I'm usually not concerned about rationalizing denominators like that, okay? Historically, it's not quite clear why that became standard practice. What the advantage to doing that is. So I just I don't care. All right, for my part. All right. Well, all right. So there's one example. This factoring technique is called, not surprisingly, completing the square. Okay. So that is, transforming, right, some integrand, right, so that it will fit into one of your inverse trig patterns. Okay. Let's try this one. Woo, this one looks fun. Okay, all right. Mm-hmm. So I'm going to help you all start this one because this one is.
For example, 2, I was just wondering, like, why you didn't take the a to be negative 1?
Why I didn't do what?
For the example 2.
Mm-hmm.
Here you said a is equal to 1. Example 8.
Yeah. Why didn't I take a to be negative 1? Yeah, because you want. We were trying to fit into the arcsecant integration pattern, right? And so you want expression squared minus constant squared, okay? So, right? So if you write a is minus 1, I guess you could do that, right? It is minus and then minus 1 squared, but that's just as kind of unnecessarily difficult, right? Okay. All right, let me show you now so this problem, there's more than one way of going about this one. But let me show you how I probably would think about this if I were just shown this problem for the first time. All right. Okay, so look, I'm thinking, look at that denominator. So I'm not initially thinking about inverse trig functions at all. Okay, so that's not at the forefront of my mind. But I'm looking at the denominator, right, x squared plus 4x plus 5, and I'm thinking it would be nice if I could just substitute for the denominator, correct? Right? So if I could just let u be x squared plus 4x plus 5. Okay? But that's really only going to work well if the derivative of that, right, is turns out okay. So what is the derivative of x squared plus 4x plus 5? That's 2x plus 4. Now, do I have 2x plus 4, though, multiplied into the integrand here? No, right, okay. But I'm really close, correct, right? Because I have 2x plus 3, right? Which is really close to 2x plus 4. So I'm thinking, I might be able to massage this problem a little bit, okay? So that I do have the 2x plus 4 here in the numerator. Well, how can I make 2x plus 3 into 2x plus 4? Yeah, I can add 1, but of course if I add 1, then I have to at the same time do what? Subtract, right, okay? All right, so let's do that. All right, so I'm going to rewrite this top as, so bear with me for a minute because it's not going to stay like this for long. But I'm going to rewrite the numerator as 2x plus 4 minus 1, right? Because isn't 3 4 minus 1? Yeah, okay. All right. Over all of this, right? X squared plus 4x plus 5. Now, I'm going to split that up into two integrals, okay? Here's the integral that I really was hoping for. And the reason I was hoping for that integral, right, is because the derivative of x squared plus 4x plus 5 is what? 2x plus 4. So how are you going to be able to integrate this? Using what technique? Well, using u substitution and eventually what will show up in your antiderivative. Log is going to show up, right? Okay? Because here you're going to have an expression divided into its derivative, correct? This is like du over u, right? Okay? If you think of this as being u, then this will be du, right? Okay? The derivative of u. So, and you integrate that using natural log. So this, we'll have to do a substitution, right? But this we can eventually integrate using natural log. Now, what about this? Okay, so don't forget the minus 1 is still there. So now I have minus, and then I have 1 over x squared plus 4x plus 5. And now you're looking at that and you're thinking, well, that's kind of almost as hard as the original problem, right? Okay, so what good have I done myself by splitting this up into two integrals? But now, what can we try here? Completing the square, right, okay? Now we can try completing the square in the denominator. You don't want to use substitution, right, okay? This is where we're going to use substitution for the denominator. Here, we are going to use substitution eventually, right, but after we have completed the square, okay? This problem now is going to look like this one, right? But this is just a standard substitution problem, all right? See, that first step now there is really important, though, okay? I was looking at that thinking that is really close to being the derivative of the denominator. If that were the derivative of the denominator, like here, I could integrate that using natural log, okay? So I'm just going to make this into the derivative of the denominator by adding 1 to the 3, but then I have to subtract 1, right, to compensate for that. Now split that up and hope for the best, all right? Okay. I'm going to do the first integral because that's the easy one, and then I'm going to let y'all try completing the square on this one, all right, and see what happens. All right, so this is easy, right? I'm going to use a substitution. U equals x squared plus 4x plus 5, right? And so du dx is 2x plus 4, right? Just exactly as I had planned, right? So dx is du over, if I can squeeze that in there, 2x plus 4. So we make that substitution, right? And I get 2x plus 4 over u. I'm calling this u now. And now dx is du over 2x plus 4. And of course, what happens now? Yeah, the 2x plus 4's cancel. And we end up here integrating du over u. And how does that integrate? Of absolute value of u, right? Okay, which is natural log of absolute value of x squared plus 4x plus 5. See, so the first part just falls apart really fast, right? Okay. Now, I want y'all to try the second part. This is where we're going to use completing the square so that we can eventually use what? Inverse trig function? Yeah, arctangent, right? Okay, inverse trig function, arctangent, right? So see if you can complete the square on this. That means you're going to group the x squared plus 4x together, right? Keep the 5 separate. Add something into the parentheses so that this will factor as a perfect square. And then make sure you subtract that same thing outside, right? Okay, and see what happens, all right? So try completing the square on that denominator, and let's see how that integrates, all right? Okay. All right, so y'all will try that one. I don't have Taylor, so y'all are going to have to help each other, okay, or work really efficiently. I'll try to get to as many people as I can, right? Start working fast because we don't have a lot of time, right? So just dive in there, okay? Did you already do it? Oh, okay. Yeah, nice, right? So you see you get this beautiful answer, right? Log and arctangent, okay? Don't you feel smart? I'll separate them. All right, so you got it to there. Now, how is that? Oh, you already did it here? I see, right? Okay. Nice. Oh, you can just drop the ones, right? Okay. Yeah, nice, right? Okay. So did you see how to complete the square, right?
Yeah. I was thinking the
Well, you can, but the way since we don't really have an equation here, the way to in effect do this is, like I said, put these together and keep the 5 over here, right? Okay. Now, what do you add in the parentheses to make this a perfect square?
So you divide the 4 by 2, and then you square the 2.
Yeah, so what would that be? 4, yeah. So you put a 4, you got that, right? Okay. So this bottom is going to be now x squared plus 4x plus 4 plus 5, but now I have to subtract what? The 4, right? Okay. So that's going to leave you with 1. Yeah, so so how does that now factor?
X minus 2 squared.
X plus 2 squared,
okay.
Yeah, be careful about the sign. So it's x plus 2 squared plus, that's just what? 1. All right, so now you can write this as x plus 2 squared plus 1. Yeah, okay. And that's sum of 2 squares. Excellent, right. So how does that integrate now?
Well, dx equals du.
Yeah, dx equals du, right? Yeah, you didn't write the dx right here, right? Yeah. So you're just going to put instead of dx du, right? Yeah. No, du, right?
Oh, yeah.
Yeah. And now it's 1 over x plus 2 is the u, right? So you have u squared plus, and then you have 1. Yeah, but a is 1, right? So it's 1 squared. Yeah, now how does that integrate? That's perfectly the arctangent, right? So how does that integrate?
1 over
1 over a. A is 1 though. So it's 1 over 1.
and then
It's u over 1. There you go. Right. That's it. But don't forget, this is being added on there, right?
Yeah.
Okay? Because you got those two things added together. Are they added? Actually, they're subtracted. Because we have a minus sign there. Did you get it? Right. So you got it in the right form. And what does that go to?
Arctangent.
Yeah. So what's altogether, what's your antiderivative then? So remember, you got the first part, right? Natural log of the value.
Would be natural log absolute value of x squared plus 4x plus 5 minus arctangent x plus 2 plus 8.
There you go. That's it. Yeah. Nice.
I'm confused now.
Yeah. So you don't subtract here. You always add in. Yeah. Right. Yeah.
Okay, I think I'm confused.
Yeah. You always add inside the parentheses and subtract outside the parentheses. Did you get it there? Yes. That's it. Right. That's nice. Plus this. Right.
Wouldn't it be make this a negative so it cancels each other out? Or
Well, negative constants and positive constants matter because they're all constants. Yeah. So you can write as plus c. Did you have it perfectly there? Yeah, right. So of course, square root of 1 is 1, so you can just drop these denominators, right? Okay. Yes. Oh, wow, y'all are so fast. Are you still completing the square there? But you're almost finished, yeah. Okay. All right, so what's your total answer there then? Because that's 1/2 of it, right? So what's the total thing? Because remember, we also had the first part, which is that natural log. So write down the whole antiderivative, right? Yes, nice, right? Okay, beautiful antiderivative there. All right, so what's there? There's a sign there missing. Right? These things are multiplied together. You lift off this, right? Okay. All right, so I see this. Where's the rest? Oh, you haven't done any more calculations. Why?
I didn't know how to start it.
Huh?
Didn't know how to start it.
Okay, you could have asked him how to start it, right? Okay. Ask your friend.
He's confused. So like you have the plus 4 right here, right?
Minus 4 there, yeah.
So this would equal what?
So how does x plus 2 squared? Yeah.
And then you find the derivative there, so it's gonna be like 1, right?
Yeah.
So it's gonna be du dx. But then
So du is equal to dx. So here you'll have, so when you make your substitution, this will just be du here, right?
Oh yeah, my bad.
Yeah, there was a dx right there to start with, yeah. But this is now u, right?
Sir.
So that you can write as u.
Sir.
So this is u. So it's 1 over u squared plus 1. Right, there you go. Right. du.
Oh, I forgot.
Yeah. And now that is perfect for arctangent, though, right? Okay.
What's the formula for like arctangent?
It's 1 over a arctangent of u over a. Like that. What's your a here?
My a is gonna be 1.
Yeah, right. Okay. So y'all did do that very well, okay? That's very encouraging. Got to be able to duplicate that on the test that well, okay? So you can't get hung up on a test. So I think most people completed the square here properly and got that this is 1 over x plus 2 squared plus 1 squared, right? Once you finish completing the square. And then, so now you can let u be x plus 2, and the a is going to be 1. And now that's really 1 over u squared plus 1 squared, right? A squared. So this integrates quite easily using the arctangent formula. It's 1 over a, which is 1, arctangent of u, which is x plus 2 over 1, and then plus a constant. So your final answer here there is looks really impressive. Okay, you get a big expression for the antiderivative. This is quite typical of calculus 2 problems. So there is your antiderivative, natural log of absolute value of x squared plus 4x plus 5 minus arctangent of x plus 2 plus a constant, right? See, nice antiderivative. It involves natural log and arctangent, all right? From that not very, kind of innocent-looking original integrand, just an algebraic expression, ends up with this natural log function in the antiderivative and arctangent in the antiderivative, okay? Really unexpected, maybe kind of antiderivative, right, for what doesn't look like that difficult a function. Okay, let's look at one definite integral. Ooh, I wonder what this one's going to end up like, okay? Because the limits of integration are kind of funny there. 3/2 and 9/4. So those are probably created just to make the calculations easier, I'm guessing. Let's see if we can work through this one. All right. So the hard part of this problem is I'm not sure what the hard part of the problem is, but the first hard thing is just trying to find the antiderivative, right, of 1 over square root of 3x minus x squared. Never mind about the, evaluating the antiderivative at the limits of integration, right? Okay. First, we have to figure out what the antiderivative is. All right. So that's kind of a separate problem. So let's go off to the side here and see if we can find the antiderivative of 1 over the square root of 3x minus x squared. So that has a square root in it, right? So that suggests that maybe we can try integrating this using inverse trig function, correct? But which inverse trig function? Arcsecant, okay? That's one possibility. But remember, in arcsecant, you have, if you're going to integrate using arcsecant, you want under the square root what? Expression squared, is that the way it is? Expression squared minus constant squared, right? You want the expression squared first and the constant squared second. But this is kind of opposite of that, right? Okay? Because it looks like the expression squared is second, right? So when the expression squared is second, that would be what? Arcsine. So maybe I want arcsine. Now, but even that's a little bit confusing. If I had 3 minus x squared, correct, that would be easy to see how to apply arcsine to integrate this, because you would have difference of 2 perfect squares, right? 3 is the square root of 3 squared, and then, of course, x squared is x squared, correct? So you would have constant squared minus an expression squared. We could use arcsine. But this is not just 3. This is 3x, unfortunately, right? So not a constant. So, see, that kind of throws a monkey wrench in the machine there, all right? So any suggestions? Shouldn't give up too quickly, okay? Because what have y'all just learned about? Completing the square, that's right, okay? So that's what we're going to try to do. We're going to try to complete the square on 3x minus x squared and see what happens, okay? So I want to take the 3x minus x squared, and I want to see if I can write that as a perfect square, okay? Not just 3 minus x squared, but the 3x minus x squared, right? Now, what's difficult about completing the square on 3x minus x squared is it's the fact that the sign of the x squared is negative, okay? The sign of the x squared is negative, and that is an issue, okay, with completing the square. So here's what we're going to do. I'm going to fix that issue, though. Let's rewrite this as minus x squared plus 3x. Of course, that's That doesn't make the minus x squared positive. But now I'm going to factor out the minus sign. Okay? So I have minus, and then x squared. What happens to this sign? It changes, right? So you have minus x squared minus 3x. This is what I want to complete the square on, okay? Just leave the minus sign in front, okay? And I want to complete the square on x squared minus 3x. So I have to add something in the parentheses here. What do you add in the parentheses? So it's minus x squared minus, it's minus outside, and then x squared minus 3x, and then plus something. But what's that plus in there? How do you find that? What do you do? What did I say do? Take the 3 and do what with it? Divide by 2 and square. So take the minus 3, divide that by 2, and square that. What does that give you? 9/4. Ooh, there's a 9/4 right there. So I'm thinking that's kind of a good sign, right? So you'll put in here 9/4. All right, so let's see what we've done there. So now I have square root of this, but I claim this factors. How does this factor? Remember, I completed the square, right? So I'm guaranteed that if I did the completing the square right, which I think I did, I'm guaranteed that this will factor as a perfect square. What perfect square will that factor? It's going to have an x in it. Okay, all right. So it's going to have an x in it. What's the other term, though? It's this. Whatever you squared, that's the other term. So what do we square to get the 9/4? Negative 3/2. Okay? So here I have minus 3/2 squared. All right, now look, be really careful, but you got to be careful here, right? This is what we started with, but remember, we added in 9/4, right? Okay? So you have to compensate for that. You have to compensate for that, right? So outside here, you have to either add or subtract 9/4. The question is, what is it? Right? See, I put the 9/4 in here, right? That wasn't there before. So outside, I have to compensate for the 9/4. So how much did I really add there? Did I add 9/4? No, what did I really add? I didn't really add in 9/4, right? What did I really add in? Negative 9/4. Don't forget there's a minus sign in front of that parentheses. So, see, I changed this expression by adding in a negative 9/4. So how do you compensate for that outside? You add 9/4, right, okay? So here should be 9/4. I'm going to put it in front instead of behind for a reason. So here is 9/4. All right, let's make sure we understood what we did. All right, that was our, this was what we originally had under the square root, right? I completed the square on that. I came to this. But I changed this quantity, right, by appearing to add 9/4. But I really wasn't adding 9/4 because this minus sign means I was subtracting 9/4. So to compensate for that, I have to now go back and add 9/4. That's why the 9/4 is right here. Is this difference of two perfect squares now? Yes, right. We have completed the square. What's the square root of 9/4? 3/2. Sure, right. Okay. 9/4 is 3/2 squared. So your A value is 3/2. What's your U? X minus 3/2. Sure, right. Okay. So you're going to just substitute for x minus 3/2, right? You're going to substitute in u. So we get, as our antiderivative, this is 1 over square root of 3/2 squared minus u squared, right? du is going to be the same as dx. So the dx here, which I dropped, is really du. And now this is easy to, well, kind of easy to integrate, right? That is, how do you integrate that? Using what function? That's arcsine, right? Because you have constant squared minus expression squared. All right, so let's see if we can write down that. In the arcsine, remember, you don't have to write the 1 over a, correct? So you just get arcsine of u over a. What's the a? 3/2, right? And then normally we would add a constant here, but we don't need the constant. But let me go ahead and add it just for clarity. So let's see. This looks like arcsine of dividing by 3/2 is the same as multiplying by 2/3. So you have 2/3 of u, but u is x minus 3/2. If you multiply the 2/3 in there, now you get arcsine of 2/3 x minus 1, right? Because 2/3 times 3/2 is 1, plus a constant. So that is the antiderivative. I didn't make a mistake there, did I? Dividing by 3/2, same as multiplying by 2/3. U is x minus 3/2, right? Multiply through there, you get 2/3 x minus 1. So there is our antiderivative. That's only half of the problem, though, because what do we want to do with this? we have to use it, right, to evaluate the definite integral. So let's see, what am I evaluating here? Arcsine of, again, it's 2/3 x minus 1. And I'm going to evaluate that from 3/2 to 9/4. Okay, so let's do it here. So first I have arcsine. First put the 9/4 in, so you have 2/3 times 9/4 minus 1, right? And then minus arcsine of 2/3 times 3/2, plug the 3/2 in for x, minus 1, right? Well, the second term is really easy there. That's arcsine of what? What's 2/3 times 3/2 minus 1? 0. That's arcsine of 0. So that should be easy to calculate. And then for the first term, we have arcsine of, what does that end up being? What's 2/3 of 9/4 minus 1? Does that work out nicely there? 1/2, yeah, okay. Ooh, I like that. So, what's arcsine of 0? So what angle, remember you're computing not sine of 0, but arcsine of 0. So what angle gives you sine 0? Sine of what is 0? Sine of what angle is 0? Look on your cheat sheet if you have to there. Sine. Okay. 0. How about 0? Yeah. 0, right? Okay. So arcsine of 0 is 0. All right. Sine of 0 is 0. So arcsine of 0 is also 0, right? Okay. What about arcsine of 1/2? So what angle gives you sine 1/2? Is it pi over 6? I think so, right? Okay. It's pi over 6. So arcsine of 1/2 is pi over 6. So nice answer there. Nice, simple answer. It's just pi over 6. Okay. Cool. All right. I like that one. So there's a little more complex version there of completing the square, all right, okay? That example might be useful on one or two of the homework problems. If you have negative x squared and you're trying to complete the square on that expression, you've got to factor out the minus sign. That makes completing the square much easier, okay? That makes completing the square easier. All right. Let's stop here for a few minutes then. I think this is our last example from applying the inverse trig functions for integration. All right, and so we've, as I mentioned, we've hit the end of our first half of integration techniques, and now we're going to look at some applications of those integration techniques before we come back and do some more advanced integration techniques. Okay. All right. So we won't be learning any new integration techniques for a while, but we're going to learn how to apply these techniques. So let's take a few minutes, and we'll come back and we'll look at our first application. Okay, which is in the subject of differential equations. In which we frequently apply our knowledge of calculus too. Okay. So we'll recommence maybe at about 10 after. Okay, so we're stepping off here a little bit into applications of integration, starting with what I mentioned, differential equations. So here's what a differential equation is. It's an equation, all right, and you solve differential equations like you solve equations, okay, except the solutions are different, slightly different. So a differential equation is an equation that involves x and y, those variables, but then also derivatives of y. So you're thinking of, at least in these differential equations that we're going to look at, we're thinking of y as being a function of x. So in our differential equation, we have the variable x possibly and the variable y possibly, but then also derivatives of y. Okay, again, derivatives of y with respect to x, because we're thinking of y as being a function of x. So here are just a couple of simple examples of differential equations, right? Okay, so again, these are equations, right? The right-hand side doesn't have to always be 0, but these are equations, right? And again, they involve, well, constants, and then the variables x and y. Notice they're showing up in the equation, and then, but here you have also in the equation derivative of y, right? Again, thinking of y differentiated with respect to x, right? Okay, so this is, I wrote that down as y prime, but we could have written that down as dy dx. It's the derivative of y with respect to x, okay? And so differential equations are just usually important in applied mathematics. They're the most important part of applied mathematics, and because many of our fundamental properties, fundamental laws from physics and chemistry can be expressed in terms of differential equations. You're going to see examples of that, okay, or at least one example of that, okay, in this section. And then, but in other sciences too, like biology and but not even science, business, okay, in other areas, then differential equations are used to model complex systems. So differential equations appear a lot even in biology, but also especially in business, okay? So many properties of finance in business can be expressed as differential equations. So tons and tons of applications of differential equations. So we'll see some applications here, but we just want to get a feel for you know, a little bit about how differential equations work and how we can go about solving differential equations. So when you say you're going to solve a differential equation, what you're looking for is that function y equals f of x, right? Okay, because again, remember, you're thinking of y as being a function of x. So you're looking for the formula for this function so that when you substitute it in the equation, it will make the equation true. right? That's always what you mean, right? Essentially, when you're solving equations, right, you're substituting something for the unknown in the equation that makes the equation true. Well, it's true in differential equations as well. You're substituting something for the unknown to make the equation true. But in this case, the unknown is not a number. The unknown is a function, all right? So you're looking for the formula for that function, so that when you substitute that formula into the differential equation, the equation will come out being true. Okay. All right. So, well, let's take a look at just again some examples of differential equations and solutions to differential equations, what those look like. Okay. Before we talk about how we go about solving differential equations, which is a really big topic. All right, of which we're just going to learn a little bit. Okay. So. So in these examples, what you're given is a differential equation, and then you're given a function, y as a function of x, and we just want to verify that the function that's given is really a solution to the differential equation. Okay. Oh, by the way, notice differential equations can involve first derivatives, so dy dx, but they can also involve second derivatives as well, all right, or higher order derivatives. This differential equation involves the second derivative of a y. Okay. Right. So notice that differential equation says something really simple there. If you kind of rewrite the differential equation by moving the minus y back over to the right-hand side, notice what that says. That says the second derivative of the function is the same as the function itself, right? Okay. That's what that's all that differential equation is saying. Okay. All right. So here we're given a hypothetical solution to that differential equation, and we just want to verify that that is true. So I just want to check, is that a function really a solution to this differential equation? Oh, by the way, now, differential equations are like numerical equations, right? Or like algebraic equations, I should say. You can have more than one solution to a differential equation, just like you can have more than one solution to an algebraic equation. All right, so this may not, if this turns out to be a solution, this may not be the only solution to this differential equation. But let's check to make sure it's even a solution. All right, so how do we do that? Well, you just have to plug that function back into the equation, see if the equation is true, right? So to plug this function back into the equation, of course, you're going to have the second derivative, right? I mean, this you can plug immediately back into the equation because y is 4e to the minus x. But to get the left-hand side here, right, you're going to have to take the second derivative of this function. Well, that's not too hard to do, right? We know how to do this now. So what's the first derivative of this function? Negative 4e to the minus x, correct? Right? Okay. Why is that? Well, what's the derivative of 4e to the what's the derivative of e to the minus x? Well, okay, let me start again. To differentiate, this is an exponential function, correct? Right? Okay. So to differentiate that, you just repeat the function, correct? But you have to remember to multiply in what? Of the exponent, right? Okay, so don't forget the derivative of the exponent here, which is going to be minus 1. So you have to, that's why the minus sign is important there in the first derivative. But that's the first derivative. We don't really care so much about the first derivative. We want the second derivative. So let's see, what is the second derivative? Well, right, you just repeat the formula again, correct? But then you have to remember to multiply in that derivative of the minus x, right, which is minus 1. So you end up with positive 4e to the minus x. So there is your second derivative, right? So of course you put those into the formula, and do these two things match? Sure, right? Okay. The original function was 4e to the minus x. The second derivative was also 4e to the minus x, right? So that's it. Okay. So there is one solution at least, right, to that differential equation. Just that simple. Let's try this one, okay? So frequently now in solutions to differential equations, because differential equations can have lots of solutions, often you'll see your solutions expressed like this. So what this solution says is that any constant times x cubed should be a solution to this differential equation. So you can get different solutions by changing this constant, right? Okay, would give you a different solution. All right, so let's check and see if our solutions really do look like this, right? So I just need the first derivative here, right? So let's calculate the first derivative of y, and that's pretty easy, right? You just use the power rule here, right? So what is the first derivative? 3 times c, right? X what? Squared, okay? So subtract 1 from the exponent. Did y'all think y'all were integrating? You didn't want to write x to the 4th over 4, did you? That's integrating, all right, okay? But here, we're taking the derivative, all right? So the derivative is 3c x squared. All right, now let's plug that into the differential equation, right, and see what happens. So I have x times 3c x squared minus 3 times y, but y is c x cubed, right? And this is supposed to be 0. So let's see, this is 3cx cubed, that first term, and the second term also looks like 3cx cubed, right? And that's definitely 0, correct? So that's it, right? This is a solution to that differential equation. So that's a general solution to the differential equation. You can get specific solutions, again, by choosing values for this constant, all right? All right, so I'm going to let y'all try one. This is very similar to this one, right? Okay. Here you have y double prime minus y equals 0. This is y double prime plus y equals 0. Ooh, but notice the solution comes out much different, okay? It doesn't involve exponential function at all. It involves trig functions, all right, instead of exponential functions. Now, what are the C1 and C2? These are arbitrary constants, okay? So you can get different solutions to, apparently, if this really is what the solutions look like, right? You can get different solutions to this differential equation by picking a different coefficient here and a different coefficient here. And the reason we have subscripts here, C1 and C2, is that indicates that these two numbers do not have to be the same, okay, right? The constant that you choose here does not have to be the same as the constant that you choose here, all right? Anytime you choose a number here and you can choose a different number here, that would give you a solution to the differential equation. Okay. All right, see if you can check that now. So you're going to have to take the second derivative of this and then see if you can plug it back in. Remember, y is all of this, right? So you're going to have to plug in, things with lots of terms in them, but see if they all cancel out and give you 0, right? That's what's supposed to happen. When you check that, if that really is a solution. So try to verify that for me. Yes? What now? You don't need the product rule here. You do not need the product rule because this is just a constant. So what would the derivative of this be? What's the derivative of this one? Yeah, what's the derivative of sine? Yeah, so you would have, for the first derivative, you would have c1 cosine x. What's the derivative of cosine? Negative sine. So that would make that plus, so you would have c2 sine of x. That's the first derivative. But then you have to differentiate again to get the second derivative, right? Okay? Because it's the second derivative that you're really interested in. Yeah. Mm-hmm.
I'm at this step, but I don't think my cosines cancel.
All right, let's see here. So what's your first derivative? c1. Oh, yeah. No, because you did this wrong, right? Okay. So the derivative of this is c1 cosine of x, but what's the derivative here? What's the derivative of cosine of x? Negative sine of x, right? Okay. Yeah. So, but it's multiplied, not subtracted. So these two are going to cancel each other. So you just get this. Now when you differentiate that, what happens? That is... Yeah, don't write it like this, because that looks like c1 minus sine of x, but this is c1 times negative sine of x. So why don't you put the minus sign over here? See, these things are multiplied, and then here, this is a plus now, right? So there's the second derivative. Now try that, and see if that works better, okay? Does it all cancel, Zhao, does it?
Yeah.
Oh, I see. Oh, there you go. Yeah. So it is 0, right? Okay. Does that cancel? I don't see. You should have some C's in here, though. Okay. But and they've got subscripts on them.
Okay,
So they're not the same C, right? C1 and C2, right? So you want to maintain those all the way through. Does it, let's see, there's plus minus. Oh, okay, right. So that does add up to 0, right? Okay. Did it cancel?
Oh, yeah.
So what canceled here? There you have
Negative
this.
sign, plus sign, and then negative cosine.
Oh, I see. Okay, right. And these are both C2s and these are both C1s. All right, okay. Does it cancel?
Yeah, I just messed up on the signs. So this becomes negative.
Yeah, and this one is also a negative. So don't write this like this, because that looks like C1 minus sine of x, but this is C1 times negative sine of x, right?
Oh, okay.
So yeah, you can't write
So
that. So yeah, put that in front, right? Okay.
Yes.
Yeah. Don't write something like C1 minus sine of x when you're multiplying. Okay. Because that means something different than C1 times negative sine of x.
So
Find the second derivative now here. Okay. What derivative is there?
So this is the first prime. Derivative and 0.
No, don't use the product rule. You do not need the product rule. You're making it more complicated. Because this is just a constant.
Yeah.
So you can just differentiate this. You don't have to use the product rule. Yeah. You don't need the product rule here, okay? Because you have a constant times the sine, constant times the cosine. You don't need the product rule, right, to take the derivative, all right, of these terms. Well, does it add up to 0? Okay, all right. So if it adds up to 0, you probably got it right, okay? All right, so let's see what... Let's see how that one works now. I think most people got it to cancel properly. That is a solution to the differential equation. So y prime is going to be, again, you don't need the product rule because this is a constant. So you can just write down C1 times cosine of x, right? And then minus, what's the derivative of cosine? That's negative sine. So I saw a lot of people writing this as the derivative, okay? That's not correct, right? This means this constant minus the sine. What you meant, though, was this constant times negative sine, correct? So don't write that like this, okay? This doesn't mean this times this. This means this minus this, all right? So if you to indicate that properly, put the minus sign in parentheses. So these are multiplied. And then, of course, the minus signs are going to cancel each other, right? So you might as well write this as plus C2 times sine of x. So what's the second derivative now? That's going to be what? Minus C1 sine of x, right? And then here plus C2 cosine of x, right? Now let's plug those in. So second derivative, minus C1 sine of x plus C2 cosine of x. Original function, C1 sine of x minus C2 cosine of x. And does everything cancel there? Yeah, nicely, right? So that is equal to 0, right? So so our proposed solution to that differential equation really is a solution. All right, so there you got just a real quick feel, right, for what differential equations are. But of course, usually what we're doing with differential equations is not checking solutions. right? Okay. What we want to do is actually find the solutions. So if we're given a differential equation, we want to see can we actually figure out what the solution to the differential equation is. Again, now this is a big solving differential equations is a big complex topic. It's more complex than even solving algebraic equations. And you know there's lots of different methods for solving algebraic equations. Well, there's just many times that more methods for solving differential equations. So this is not an easy subject to master, all right? So for some of you, you'll be going on to take a whole course in solving differential equations, okay? But let's look at some fairly straightforward differential equations that we are able to solve, starting with this one, okay? So that one doesn't look too bad, right? We have y prime there is equal to 2x divided by y, okay? And so we want to see if we can figure out what is that formula for the function y that will satisfy that differential equation, if there is one, okay? I guess differential equations don't have to have solutions any more than algebraic equations have to have solutions. All right, so here's the technique that we're going to use here, and for our differential equations, we're going to use a technique called separation of variables. And when it works really nicely. In many situations, it doesn't work, but I think for all these equations that we'll be solving here, these easy equations we'll be solving, this technique will work. So what separation of variables means is just what it says. You want to get all the y variables on one side of the equation, and you want to get all the x variables on the other side of the equation. Okay, that's the first step. All right. Now, one thing I'm going to do first here in order to simplify that process of separating the variables is I'm going to take the y prime and I'm going to write that in, that's a derivative, right? I'm going to write that in the old-fashioned notation for derivative, dy over dx, okay? And the reason I'm doing that is I want to remind myself that y prime does involve a little bit of x, right? Okay? Because y prime means dy over dx. So when I separate the variables, I've got to get the dx away from the dy. That's part of the process of separating the variables. All right, so can y'all tell me how to do this here? So is that going to work? So I need to get all the x's on one side. Let's put them on the right. And I need to get all the y's on one side. Let's put them on the, let's see if we can put them on the left. All right, so any ideas here? Multiply dx on both sides? Yeah, okay. So that's a good first step, right? To get the dx's over to the right-hand side, right? And then, so that would give me what? Dy is equal to 2x dx over y, and now I got to get the y back over to the left, right? But that's pretty easy to do, right? Just multiply both sides by y, right? Okay. And so, well, what do we end up here? We end up here with y dy is equal to 2x dx. And what do those things look like? Both sides of that equation. They look like, well, what I was thinking of is, I guess you could say a lot of things that they look like, but what I had in mind is those look like integrands, right? Okay, right? They look like things you would have after an integral sign, correct, right? Y dy and 2x dx. So what I'm going to do is integrate both sides of this equation now, okay, right? So, I mean, I guess since these two expressions are equal, then their antiderivative should be equal as well, right? Okay. So now I'm going to integrate both sides. Wow, can we integrate these? I think you can integrate this one really easily, right? Okay. What's the antiderivative of 2x? Yeah, 2x squared over 2, sure, right? So the 2's will divide out, correct? But let me write it down first. So here we have 2x squared over 2. You're going to use the anti-power rule, right? So you don't have to do anything fancy here to integrate this. It's just 2x squared over 2. Don't forget now, you have to add in a constant, though, right? Okay? And because these are not definite integrals, these are indefinite integrals. What about over here? This is just as easy. What's the antiderivative of y dy? It's y dy. So when you integrate this, you just get what? No. What? Y squared over 2, right? Okay, it's the anti-power rule again, right? Okay, it's going to be y squared over 2. This and this are the same, right, except the 2. Plus a constant, correct? Now, these two constants do not have to be the same because these are separate antiderivatives. So this constant I'm getting ready to add here on the left-hand side doesn't have to be the same as the constant on the right-hand side. So we need to indicate that we can have different constants. You do that with subscripts, okay? So I'm going to call this one C1, and I'm going to call this one C2, or you could reverse it. It doesn't matter. But you've got to make it clear that not the same does not have to be the same number. So let's call this one C1 and this one C2, right? Now remember, of course, these two's divided out, so really on the right-hand side you just have x squared. Now, remember, my goal, what is my goal? I lost sight of it there. Now find C, right? Okay. Yeah, what is the solution here again? We want to write down what? An equation for what? Y, right, yeah, okay. We want an equation for y, right? My solution is y equal to some formula, right, involving x. That's what my goal is. So let's see, how can I get that from this equation? I guess just try to solve for y, right? Okay, so, well, let's do that. So I have y squared over 2 is equal to x squared, right, plus C1, and now I'm going to subtract the C2 from both sides, okay? So we end up with this. Okay, now here's a simplification I can do at this point. Here you're taking this constant, which is just some arbitrary constant, and there you're subtracting off some arbitrary constant. So you can combine those two constants, right, and you get just a third constant, correct, right? Okay, so let's go ahead and combine these, and let's give that a name. You don't have to use C3, though, okay? You could use C3, but since C1 and C2 are going away, let's just use C, okay? So these two constants combine to give me some third constant, right? All right, so we got that far. Now I got to get rid of the 2. That's pretty easy to do. Just do what? Multiply both sides by 2, right? Okay, so you get there 2x squared plus 2c, right, is y squared, right? And now how do you finish solving this for y? I think y'all know how to do that. What? Take the square root, right, okay? So y is going to be square root of 2x squared plus 2 times this constant. By the way, if you want to, 2 times the constant, by the way, is another constant. So you could just write this as c, okay? But let's leave it written like this. Let me remind you here, though, that when you take the square root of a quantity, quantities can have 2 square roots, right? So what do I need to put here in front of my plus or minus? That's right, okay? So I get 2 possible formulas for this, for the solutions to this differential equation, right? One of them would be y equal to the positive square root of 2x squared plus this. And then the other one is y equal to minus square root of 2x squared plus this constant, okay? So there's 2 possible solutions to the differential equation, and actually there are lots of them because you can get other solutions by changing this constant, right? Okay? So lots and lots of solutions to this differential equation, but they all have this format. Yeah?
Would it have been wrong if you decided it was like a negative constant?
A negative constant here?
When we combine the two in the like second.
No. Here, if we wrote this as a negative constant, no, it wouldn't make any difference. Because if you wrote negative constant, you could always get a positive number by making the constant negative, right? Then you have minus, which is plus, right? Also, you really don't have to write this as 2c, okay? Because twice a constant is it's just another number, right? So you could have just written it as c, right? This 2, though, I think is important, okay? All right, this 2 you cannot drop, all right? But this you can just write as c, just plain c. Okay. You cannot, however, let me not get into that. All right, so I was going to say something else that looks like you could do, you cannot, but I'm not going to bring that up. All right, well, okay, so see how we work through that, right? Okay, but the key step is separating the variables, all right? Separating the variables. So I wanted to get all the x's, including dx, on one side, all the y's, including dy, on the other side, okay? That's the key thing. Let's try this one, all right? Or at least get started on this one. Yeah?
So combining c's, it doesn't really matter what sign it is?
No, combining c's, no, because a negative constant is still a constant. Right? Okay. I mean, if you have negative constant, you can make that positive by choosing the constant negative, right? And then you have minus, which is plus, right? So it's not important. Okay. Well, let's see how to start this one. So again, let's write the y prime as dy over dx. That's going to help you with the separation of variables part. Because it looks like you don't have any x's in this equation, right? But you really do with the dx, all right? Now, what's next there? So, well, let's see. I would have dy over dx is equal to 2y. And what can I do here? Can I multiply both sides by dx, right? To get the dx on the right-hand side? So I get dy is equal to 2y times dx. And now I want to get the y over the right. So divide both sides by y. So it looks like I have 2 dx is equal to dy over y. There you go. That's separated, right? All the y's are on one side and all the x's on the other side. Now what are we going to do? What do we do up here? Integrate, right, okay. Now we're going to integrate. See, this is where our integration techniques are going to help us. So now we're going to integrate. And now y'all can do this like so fast, all right? What is the antiderivative of here? Natural log, that's right. Natural log of what? Absolute value of y, right? Okay, plus constant. What is the antiderivative here? 2x, right, plus oops, it's a different constant. So now I have to start naming my constants. Now you really are in great shape, okay? The dy's and dx's are gone. So notice that the derivatives are out of the equation now, okay? So you don't have any derivatives anymore. So this is really not a differential equation anymore, right? But I still have to solve this for what? Y, right. So I got to solve that equation for y, okay? Ooh, wow. How do I solve that equation for y, all right? Well, I think y'all know the steps, but it's going to take us, it takes 3 or 4 steps, though, to get through this. So we're going to resume this next time, okay? So we learned how to separate variables. We learned how to get rid of the derivatives out of our differential equation. Now, how do we take this equation and solve it for y, okay? That's really just an algebra problem. The calculus part of this is gone, okay? But it does require a little bit of algebra to solve this equation for y, okay? All right. So I'll see you again on Wednesday. Now, again, it doesn't look like I'm going to have the test, so be patient. Did I not pass the... Oh, damn. Okay, well, I didn't pass the rollout, so much for that. Y'all forgot to remind me. So it may be Monday before we can have the test back. All right.